Good morning, class. I was just writing you an announcement on the web's, the laboratory Sakai site about your final laboratory exam. I call it a practical exam. Dr. Murphy calls it a practicum. I'm not sure which is better or if it matters, but it's 3 parts, and there are 2 tasks, challenges that we've created for you to carry out using the tracker software, and in conjunction, the second one in conjunction with a simulation that I've coded up in Trinket.io, and the third part is a quiz. So each part is, well, the quiz is 24 points and the other parts are 24 points in total, but altogether, the points don't really matter as much as the fact that this final practical exam is 20% of your laboratory grade. Big thing that you should keep in mind is that with this quiz for the practical exam, you only have 1 submission. You can't submit and then correct your mistakes. Just 1 submission. But you have unlimited time, open books, open notes. Go back, look at your old work, look at the old laboratory assignments from the past. But you are not allowed to collaborate with anybody else. And if I see any evidence of illicit collaboration, that would be bad. That would be bad. Okay. So you have 2 weeks from today. It's due December 4th. That's when the assignment closes. And good luck. All right. So today, I got some new material to talk to you about, and then that's it. So tomorrow we will not have a laboratory synchronous session, since it's the laboratory exam. I don't have anything to tell you. You are going to carry out this laboratory practical based on the knowledge that you've gained throughout the semester. If you have any questions, you can send them to me, direct any questions toward me. But yeah, we will not have synchronous lab tomorrow. I forgot to put that in the announcement. I'll have to send out a separate one for that. All right. So I will see you again, but it'll be after Thanksgiving. It'll be the Wednesday after Thanksgiving is the next time I'll see you, but I'll have something scheduled. It'll probably be a Zoom session instead of a live stream, so that we can have, I can take your questions more readily, okay? Because it'll be review. That's what's going on that week. All right, I posted all kinds of review materials for you on Sakai for the final exam. It is cumulative, and it is 20% of your final grade. And it could be 40% of your final grade if you do better on the final exam than you did in a previous exam. All right, enough about that. Let's get down to it. So I want to talk about the torque and the idea that torque is a cross product in a little bit more detail. So torque is mathematically defined. It's a vector, and it's defined as this cross product between an r vector, which points from the axis of rotation to the spot where the force is applied on an object, and the force vector. So it's this cross product. And let's one thing about the cross product is that the result, so you have 2 vectors, r and f, and these 2 vectors define a plane. So r and f, that's not plus, I'll just write it like this. R and f define a plane. And so, for example, I could have, maybe r points along the x-axis and f points along the y-axis. And so the xy axis, these Cartesian coordinate system, x and y, defines a plane, the xy coordinate plane. That's what I mean by that. So these two, it doesn't matter what direction the two vectors point. They don't have to be perpendicular to one another like I drew x and y here, but it defines a plane. There's a plane that goes through both of those lines. And what's true is that the result of a cross product, in this case torque, is going to be perpendicular to that plane. Another way of saying that is the result of a cross product is perpendicular to both of the vectors that you're crossing together, in this case R and F. So you'll see this again, you'll see the cross product again next semester. You'll see it when you talk about the force a magnetic field exerts on a moving charge, and it'll be the cross product between a velocity vector and a magnetic field vector. Okay, so you're going to see this again, so it's worth, you know, diving in a little bit deeper here and exploring this a little bit more. All right, so what that means is that if you have a cross product like this, where, you know, let's say here's R, so along the x-axis, okay, that's R, and I'll draw green F, let's say F is along the y-axis, like that, then that means that the cross product is going to be along the z-axis, coming out of the page like this. The torque vector will come out like that. So, so remember this notation means out of the board or page or whiteboard, whatever, and that notation means in. So I'm drawing three-dimensional coordinate system here, but I'm trying to show you that z is coming out toward you. Okay, so the positive z-axis is out of the board. The negative z-axis would be into my my whiteboard here. Okay, so let's get down to, you know, what if these vectors had actual values? So let's say r equals 5. I'll just won't, you know, it has units 2 meters, but let's just say r vector is 5 I hat. So it's 5 units in the positive x direction, and f is let's do 4 j hat. So it's 4 units, which would be newtons in this case, in the positive y direction. Okay, so if you think about these two vectors crossed together, they're perpendicular to one another, and then the result is tau, and its component is going to be pointing out toward you. That would be k hat, the positive z component. So you multiply them together, you get tau equals 4 times 5 is 20 units k hat. So k hat is perpendicular to both I hat and j hat, these unit vectors. Okay, so let me show you. All right, here's my right hand, and we talked about this this idea that you can use your right hand to orient vectors in space, and these are called right hand rules. So we talked about, like, if you grab the axis of rotation of a spinning wheel so that your fingers curl in the direction of rotation, your thumb points in the direction of the angular vector quantities, omega. Today, hopefully, we'll talk about angular momentum, and this reflect, and that vector for omega, the angular velocity, always points either. It always points in a direction that's along the axis of rotation, and because there's two senses of rotation, this is why we're doing this, because the wheel could rotate counterclockwise, looking down from above, or clockwise, looking down from above. And the result that has on this right-hand rule is it flips the direction your thumb is pointing. Okay, so here's another incarnation of a right-hand rule, which I used this one before, where I said, well, point your fingers, figuring out torque, point your fingers in the direction of the r vector so that your palm points in the direction of the F vector and then your thumb points in the direction of the torque. That's fine. I think that's the way your book asks you to proceed. I like this better. So I use my pointer finger, my middle finger, and my thumb, and my pointer finger is the first vector, which in this case is R. And if you want to practice this by putting an R on this finger, that's fine by me. Your middle finger is the vector that you are, the second vector in the cross product, which in this case would be F. So pointer finger's R, middle finger's F, and then your thumb is the result, which would be tau, torque in this case. Okay, so if you think about, so practice this now. Point your finger in the direction of R, your index finger in the direction of R, the blue vector here, and then rotate your hand so your middle finger's going up the direction of F. And what you should see is that when you do that, your thumb points toward you. It points out toward you, just like I've drawn it here. Okay, so these three fingers, pointer finger for R, middle finger for F, thumb for torque, shows the relationship between the directions of these three vectors. And your thumb, I mean, you could, the angle between R and F can change, but the thumb is always perpendicular to those two. It's always perpendicular to that plane. All right, so let's think about another example here. What if you have a situation like this? You have R now has an X and a Y component. So it's 5I hat plus 2J hat, and F has the same Y component, but now it also has an X component, 3I hat plus 4J hat. So what would that look like? Well, there's X, here's Y, and Z is out of the screen toward us. So now R is positive 5 in the X direction, positive 2 in the Y direction, so it'll look something like that. And F is positive 3, positive 4, so it looks something like that. And if you think about the right-hand rule, the result, so F and R are still in that XY plane. So if I point my index finger in the direction of R and my middle finger in the direction of F, the angle between my index finger and middle finger are a little bit less. Like this. Rotate it so you can see. But my thumb is still pointing out of the screen. So tau, in this case, would still be a vector that points out like this. It'll be a little shorter in this case because the angle between those vectors is less, so the cross product will result in less. But we can, one way we can think about this is we can break it into components. And if you think about the I and the J components, because of the way the cross product works, the I component of F and the I component of R, the cross product between those two components would be 0. Because, so remember, the cross product involves an angle between two vectors. So if you have two vectors which are parallel with one another, and I'm saying the I components, the X components of these vectors are like this, they don't contribute. So you would have, you could think about sort of doing the pairwise multiplication, pairwise cross product between the components of R and the components of F, and there'd be 4 different combinations. You could do I cross J, J cross I, J cross J, pair up the components, but 2 of those would just evaluate to 0 because their cross products involve angles between those vector components that are 0, so they don't contribute. But so it would be the 2 that would contribute, though, to the cross product of tau would be the I component here I'll draw it in here, the I component of R and the J component of F. Okay, so they would look like this. J component's in the positive y direction, so that would be a component. Point my finger in the my pointer in the positive x direction. My middle finger goes up the positive y direction, and my thumb comes out. So the R component, so this component crossed into this component, gives me 20 k hat. Okay, and now if I think about the other way, well, the J component of R crossed with the I component of F. Now I point my pointer finger up the y-axis, and my middle finger goes right, and that rotates my hand so my thumb points into the screen. So that would be a negative component to the torque. It's going in the negative z direction, and that would be this multiplied by this is 6, negative 6 k hat. So the total is positive 14 k hat. Okay, so read about. Sorry, I think someone's printing. It's my ancient printer over there. You think about the cross products. Read the section in the textbook on the cross product. There's lots of examples to clarify this, make this more clear for you. But there is a mathematical shortcut. So this is a pretty simple example that involves an R and an F vector that have just two components, I's and J components. But what if you have a full three-dimensional situation? Now you don't have just 4 combinations, you have 9 different combinations, and it could be hard to keep track of just using your right-hand rule. So there's a shortcut, and what it involves is calculating a determinant, which is a matrix operation that comes from linear algebra. So I'm going to show you how that's done. And becomes a shortcut for calculating cross products. Okay, so I got to give myself lots of space here. So the cross product that we are doing here, just to remind you, is we're finding torque, which is R cross F. Okay, so vector product, and the result of that cross product is the determinant of this matrix, where the first row are the unit vectors I, J, and K. The second row are the components of R, Rx, Ry, Rz, and the third row is the X, Y, and Z components of the force vector. Okay, so a determinant is a matrix calculation, and the way you would do a 3x3 determinant like this is you start with you're going to start with this term, and what you do is you multiply that term. That term will end up eliminating. If you focus on the I hat term, and then you cross out the other terms in its column and row, and then you calculate the determinant of the submatrix that's left over, which would be that corner. And then you turn your attention to J, and you cancel its column and row, and you just focus on the determinant of what's left over. So let's back up. Okay. So then you focus on J, you cancel its row, and you focus on the determinant of what's left over. And then you go to K, you cancel the rest of the values in its row and column, and focus on the determinant of what's left over. Okay, so if I write that out, Oh, and there's, so it would be I hat times the determinant of the submatrix that's left over when you eliminate the row and column. So you can see what's happening here is the x component, the I hat component of the result, depends only on the y and z components of the two vectors that you're crossing together. That makes sense. That comes from the perpendicular nature of the result. I hat is perpendicular to j hat and k hat, so only the y and z components contribute to the x component of the result. And there's a little rule here where the second term is subtracted off, so it's plus I hat submatrix minus j hat submatrix. So if I get rid of the elements in the second column in the first row, okay, so now I see that the y component of the result depends only on the x and z components of the two vectors I'm crossing together. And then the last part is k hat times rx, ry, fx, fy. Okay, so what are the determinants of these 2 by 2 matrices? Well, what you do is you multiply the diagonals and then you subtract off the other diagonal to evaluate the determinants. So this is going to be ry fc minus rz fy. So now you could use the right hand rule to see that this sign here makes sense. That this sign here makes sense because point your index finger ry in the positive y direction, and then your middle finger fz out toward you on the positive z axis, and your thumb points to the right. That's the positive x axis. So this first part contributes positively to the x component. Now let's do the second one. rz points out toward you, fy points up, middle finger up, and then your thumb points left. That's in the negative x direction, so you get a negative component. All right, and then this minus sign is going to flip everything around eventually, but let's write this out. So you can think of this determinant as just a way to order the evaluation of this cross product. Okay, and when you're done, well, let's flip the sign in the middle there. Ooh. All right, and make this a plus. So the y component, and then we got to flip these terms around in here. Okay, so the result that we see is that, again, what I'm doing here is that this is the answer for finding the torque, the cross product between two vectors, if those vectors have x, y, and z components potentially. And what you see is the x component of this result, the first term here, this would be the x component of the result, torque, doesn't depend on the x component of the two vectors that are being fed into the cross product. The y component of the torque doesn't depend on the y component of r and z, and the z component of the torque doesn't depend on the z component of r or f, because those components would evaluate to 0. Okay, the result is perpendicular to the inputs, and here I'm just decomposing it into the x, y, and z components of the inputs to show you the x, y, and z components of the result. Okay, so if we look at this and look at our work back here, R and F didn't have any z components, so any terms that have z components in them would be 0. So that would be 0, that would be 0, this would be 0, that would be 0. So there's no I or j component of the result, and then we just have Rx times Fy, which is 20k, hat, minus Ryfx, which would be 6k, which is the exact same result that I got over here. Okay. So one of the reasons I'm doing this now is to expose you to this cross product now, because you'll see it again next semester. And when you see it again, it'll be, well, hopefully easier for you to deal with. And fundamentally, you know, what this is a way of summarizing the calculation of cross products between two vectors, and a way to summarize the effect of the right-hand rule in these three dimensions. Okay. So right-hand rule one more time. This is the first vector. Pointer finger is the first vector. Middle finger is the second vector. So in this case, torque would be R cross F gives us tau, torque. So I can rotate my fingers, my hand, to point in the direction of R, and then the direction of F, and whatever direction my thumb points, that's the direction of torque. All right. One more topic. All right. So this is the topic of angular momentum. Okay, so let's revisit linear momentum first. Linear momentum is P equals mv. Okay? So now at this point you can probably guess what angular momentum looks like. Angular momentum isn't P, it has the symbol L, but it's a vector quantity. And in this rotational domain, rotational mechanics, what quantity takes the place of m, mass, in most of our physics equations? It's not mass, it's rotational inertia. And what takes the place of v, linear velocity, in the angular domain? It's omega. So angular momentum equals rotational inertia times angular velocity. It's a vector, so it points in the same direction as omega, which you can determine using this version of the right-hand rule. Grab the axis rotation, so your fingers point in the direction, curl in the direction the thing is rotating. Your thumb is going to point in the direction of omega, the angular velocity, and the angular momentum. Okay, so there's a lot we can do with angular momentum. And much of this is based on the fact that just like linear momentum is conserved when you have interactions that exclude between parts of a system, and we were dealing with collisions predominantly, where the system were the two objects that were colliding. So you can have collisions between objects, interactions between objects, but the fundamental property of those interactions is that in the absence of external influences, external forces acting on the parts of that system, linear momentum was conserved, which means it didn't change. The total momentum you had was the same throughout the entire evolution of that system, before the collision, after the collision. And that idea extends into this rotational domain. Angular momentum of a system, let's say you have a system that's composed of, well, let's think about a figure skater. Ever seen a figure skater do one of those spins? I think there's a fancy name for it, paré or something like that, paré, French word. And when they do one of these fast spins, that figure skater is the system, and the figure skater has angular momentum because the figure skater has mass. That mass is distributed about an axis of rotation. Um, so it has rotational inertia, has moment of inertia, I, and there's an omega. There's an angular speed, angular velocity. So the figure skater has angular momentum. And of course, there are external influences on the figure skater, like friction between the ice and the ice skates. But if all that is negligible, which over relatively short time, it's ice too. It doesn't have a huge amount of friction over relatively short time frames. It is the angular momentum of a spinning figure skater is conserved. Okay, which means it doesn't change. So let's consider the situation. So this is going to be fun. I'm going to draw a figure skater. Okay, so here's the figure skater. Arms outstretched. One leg on the ground, the other extended out, so that this, and the figure skater is spinning around in a circle. Okay, so this figure skater has a rotational inertia, moment of inertia, I, and this figure skater has an omega, an angular velocity. So put those two things together, and the figure skater has an angular momentum equal to its rotational inertia I times its angular velocity omega. I1 omega 1 equals L1. Okay, so now the figure skater changes his or her body. So the figure skater does something like this. So still, one foot on the ground, but now the other foot was pulled in, and the arms were pulled in. Wow, that's really bad. And now what does that do? All right. What does that do? You tell me. Some of you, probably maybe all of you, have observed this on television or real life. Figure skater doing one of these spins pulls his or her arms and legs in close to her body, his or her body. And what does that do? Gets faster, right, Maddie? The figure skater starts to rotate faster. So the figure skater has his or her arms out, and when he or she pulls them in, legs in, spins faster. Spins faster. How is this happening? How is this happening? If we think about this in terms of angular momentum, what effect, okay, if you have mass and it's out here far away from your axis of rotation, and then you pull it in close to the axis of rotation, what effect does that have on your rotational inertia, I? Remember, I is, in integral form, it's the integral of all the little tiny pieces of mass, dm, times the product of how far away that mass is from the axis of rotation squared. So what effect would pulling in your arms and legs have on I, the rotational inertia? Definitely decreases the radius, right? So you pull mass in, that's going to decrease I is going to get smaller. So over here, the act of pulling your legs in, arms and legs in, makes I get smaller. The figure skater has decreased his or her rotational inertia. But if angular momentum is conserved, that means it's the same before and after. So you have the situation where I1 omega 1 equals I2 omega 2, but the figure skater has done something so that I2 got smaller. Well, the only way one term in a product can get smaller but the product remains the same is if the other one gets larger. So omega 2 increases. And that's spinning faster. So the act of decreasing rotational inertia increases rotational speed, angular velocity. The figure skater spins faster. Okay? So that's conservation of angular momentum in a nutshell. You can extend this to situations where you have multiple things spinning in multiple directions. And the total, you can have angular momentums that point up, angular momentums that point down. Sorry, right hand, point down. And a change in one results in a change in the other. And so, so how are these things happening? What's happening is, you think about a collision in linear momentum. The interaction is governed by forces that are internal to the system. You have two objects in the system, they collide. A pushes on B, B pushes on A. There's that interaction, there's a symmetry there. So in rotational mechanics, the interactions are still forces, but we describe them as torques. And so you have torques that are internal to the system that are causing the changes in these quantities, angular velocity, in this case, for example. So there's a strange thing that happens here. Let's see if you can figure this out. Okay, so angular momentum is conserved, but if we think about, let's use yellow. Make it a little thicker. Rotational kinetic energy equals 1/2 I omega squared. Okay, so the initial rotational kinetic energy is 1/2 I omega squared. After the figure skater pulls in arms and legs, now the rotational kinetic energy is 1/2 I2 omega 2 squared. Okay, so if you think about conservation of angular momentum, if let's say if I2 was half I1, then that means omega 2 is 2 times omega 1. So if one increases by a factor of 2, the other decreases. Oh, sorry. I didn't switch this back over. I apologize. So I wrote out, darn it, rotational kinetic energy is 1/2 I omega squared. So before the figure skater pulls in his or her arms, there's rotational kinetic energy equal to 1/2 I1 omega 1 squared. And then after pulling in his or her arms, now the figure skater has rotational kinetic energy 1/2 I2 omega 2 squared. But if you think about, so let's think about how they change relative to one another. Because angular momentum is conserved right here, if I2 decreased by a factor of 2, was halved, that means omega is going to be doubled. If one increases by a factor of 2, the other decreases by a factor of 2. If one increases by a factor of 3, the other decreases by a factor of 3. There's that proportionality. Okay? But if you think about this situation down here, if I was halved, but omega was doubled, you're going to have an imbalance here. These are not going to be equal to one another. It's because omega is squared. So in this scenario that I just set up, the rotational kinetic energy of the figure skater after pulling his or her arms and legs in is greater than what it was originally. So the figure skater, when the figure skater does a fast spin and pulls arms and legs in and starts spinning faster, the figure skater gained energy, gained rotational kinetic energy. The figure skater gained mechanical energy. The figure skater's rotational kinetic energy increased. Where does that energy come from? Get you stumped now. Where does that end? This is the last question of the semester for new material. Where does that energy come from? What the heck? How can the figure skater gains rotational kinetic energy? That's mechanical energy. How? Where does that energy come from? Where did that mechanical energy come from? There's no external. It's not like there's someone pushing on her. There's nothing external that's contributing to that gain. Everything is internal. Tyler says Z came from. I'm not sure. So from the Z axis, from Z particles, the Z. I don't know, dimension. what Z mean? No, it didn't come from Z. Where does mechanical energy always come from? If you are accelerating, a car from rest, it's gaining kinetic energy. Where does you think of the work energy theorem? Where does a change in energy always come from? Where would you trace it to? Energy, and the other side of the equation is, we'll say it again, work energy theorem. Energy is one side. So velocity change is what is how this increase of energy manifests itself. It's rotational kinetic energy. So it's energy of motion. And that increase of energy manifests itself by an increased velocity. So Holly's got onto it now. Work energy theorem. So when a force does work, that can be the result of that can be a change in kinetic energy. In fact, that's the most fundamental expression of the work energy theorem, is that when you have a net force that does work, there's a change in kinetic energy. The net force equals change in kinetic energy. Okay, so if we dig down a little bit more, this means that the energy doesn't come with this figure skater. The energy doesn't come from nowhere. There is work being done, and that work results in an increase in rotational kinetic energy, which is a kind of mechanical energy. So work is done, and that means there's more energy. So who's doing the work? Who's doing the work? What's doing the work? It's a force. Work is a force that's applied over a distance or a displacement. Who does the work? What does the work? What exerts a force? What's moving? In the figure skater's world, in this fast spin, what is moving? What forces are being exerted to create that movement? What is exerting that force? Have any of you ever done this? Ever any figure skaters out there? I guess you could do this on roller skates too if you were really good. You could do it on a spinny chair. In fact, if we were meeting in person, I would do this for you guys. I'd have a volunteer sit on a spinny chair holding masses in their arms, and then I'd spin them, and then I'd have them pull the masses in, and they would spin faster. And you ask that person what that experience was like. Yeah, you pull your arms and legs in, and that takes effort. So if you ever did this, the act of pulling your arms and legs in does work, because your muscles exert a force over a distance, and it's not it requires effort. So you pulling your centripetal force, that would be a center pointing force, but it would be in excess of what is necessary to maintain circular motion. But I guess you could call it a center pointing force, but it's not entirely the same thing. It takes effort to pull your muscles, it takes effort to pull your arms and legs in when you're spinning, and that's work. That's a force exerted over a distance, and the result of that work is more kinetic energy, more rotational kinetic energy. So it didn't come from nowhere, it came from muscle energy. Metabolic energy stored in your cells, released, converted into mechanical work that increases your kinetic energy. Okay, so you're liberating cellular energy to create rotational energy. That's what a figure skater is doing. All right, so that's it. So again, no meeting tomorrow for lab. The lab practical exam is posted, 3 parts. 2 parts involving tracker. One of those parts also involves a simulation. And 24 multiple choice questions, which is the quiz portion of that. And you only get 1 chance for submissions on that. So please, you can save your work, but don't submit until you're convinced you got the best answers to all those problems. And it's an individual exercise, so no collaboration. And good luck with that. All right. Do you guys have any questions before I sign off for today? Don't see any. All right. Then I will see you after Thanksgiving. All right. Bye-bye, everybody. See you a week from Wednesday. Have a great Thanksgiving. Stay safe, and I'll see you then.